All right, so section 3.6, graphs of the other trigonometric functions. Now I'm prepared, this is actually my second take, I'm prepared to make some mistakes through here, so apologize if you have to go back and erase something, but this will be just like being in class with me as your human instructor. All right, so we're going to be working with tangent, secant, and cosecant, and cotangent throughout this section. Now, we already did cover this in class, so I'll try to give you more detail than I gave you there. But yeah, so we're going to just dive into this. So remember that tangent is defined as sine divided by cosine. Secant of x is defined as 1 over cosine of x. Cosecant is 1 over sine of x. And cotangent of x is cosine of x over sine of x, or sometimes more usefully, 1 over tangent of x. That being said, everything we know about sine and cosine is going to enable us to do the things we need to do to determine some things about these graphs. Okay, so here's some more details. So since sine of x is equal to cosine, or since tangent of x is equal to sine of x over cosine of x, tangent of x is equal to 0 whenever sine of x is equal to 0, and tangent of x is undefined whenever cosine is equal to 0. So we'll have asymptotes and x-intercepts respectively. Okay, when sine is 0, we'll have x-intercepts at those values, and when cosine of x is 0, then we will have asymptotes at that point. All right, so here is what this should look like. So I'm going to graph all of these. So sine of x goes from midline to peak to midline to trough to midline. Let's just sketch that. Now, cosine of x, I'm going to use x's to indicate this, goes from a peak to a midline to a trough to midline to a peak. So, according to this definition, whenever cosine of x is 0, we have asymptotes. So where cosine is 0, we're going to have asymptotes. Whenever sine is 0, we will have x-intercepts. So I'm going to put those points there. Now, given that our function is going to approach these asymptotes, that means we have some behavior, kind of like we had with rational functions, where we approach those places. So, and of course we have more asymptotes that we would approach on the left and the right. Okay. Now another thing we can think about is the unit circle, because that's always something we can hang on to. And as your angle opens up, as we open an angle up, we start right here. If we have the angle of 0, that is 0 radians or 0 degrees. That is a tangent of 0 because the slope of that line is 0. As it opens up, we increase. We increase to a positive slope, eventually approaching the positive y-axis, which is undefined. So we go from 0, increase to undefined. Then just past that, we have undefined, and then we have it's very negative, and then it starts decreasing, approaching 0 again. So that's what's happening here. Starting at 0, it increases without bound, is undefined, and then is very negative, and then it increases to 0, and then it continues increasing. So that's actually what's happening here, if you think back to your unit circle. So that is tangent, the purple lines there. I've never been able to draw those very well, so I don't expect my graphs to look very great. But the features will be correct. We have our x-intercepts, we have our vertical asymptotes, and we have that asymptotic behavior. Okay, so some general features of y equals tangent of x. The first that is very notable is that the period is not 2 pi, like it is for many of our other functions. Right. Tangent, the period is pi, because if you think about when those will start repeating themselves, we have positive, negative, we have positive again, then we have negative, positive, negative, positive, negative. So every pi, every 180 degrees, we come back around to those values. Now the domain is all real numbers x, where x is not equal to pi over 2 plus pi k. So pi over 2 We have our first asymptote, negative pi over 2 and positive pi over 2. And then every pi after that, we have another asymptote. Now the range, as you can tell, it is asymptotic. It approaches positive and negative infinity, different ends. So it has a range of minus infinity to infinity, and those asymptotes are at the places where the function is not defined. And then because of all this, it is an odd function. Just notice the behavior to the going upper right and then lower left from 0. It's definitely an odd function. We've talked about that before. And here are some key points that we can think about. So 0, 0. And again, this is on the unmodified. There's no stretch factor, no changes to the period, none of that. When you have that function, 0, 0 is a key point. All right. So 0, 0, one of those ones we graphed. The asymptotes at negative pi over 2 and pi over 2, those are two key, this shouldn't say points, that should be features. Key features include those two asymptotes, this point, and then we have the point negative pi over 4, negative 1, and pi over 4, positive 1. And then we can fill that in with that. So with sine and cosine, we have 5 features. We have our, well, 0, right? 1, 0. We've got root 3 over 2, 1/2, root 2 over 2, root 2 over 2, root 2 over 2. 1/2, root 3 over 2, and then 0, 1. Those are our 5 points, our key points in the first quadrant. Well, the sine graph has a midline, peak, midline, trough, midline. There's 5 features. Cosine, peak, midline, trough, midline, peak. 5 features. It only makes sense that tangent would also have 5. But 2 of those are asymptotes. That's where the cosine is equal to 0. Okay, now when we start stretching this, all those features actually change. But if you notice, they all change by a factor of b or a factor of a. So I'm going to actually slide right past this. But these are facts for the function a tangent of bx. All right, we're going to graph these a little differently, but those are some key features we could use there. All right, so for our first question, we have graph f of x equals 3 tangent of pi over 6x. Well, notice we have it's not really an amplitude, it's the value a. Our stretch factor is what that is. But we can think of that as kind of how our amplitude worked with sine and cosine. And then we have pi over 6x right here. So this is b. So our period is pi, not 2 pi, although you'll want to write that just like I do. Pi over the absolute value of b. Pi over 6, and that would be pi times 6 over pi. So the period is 6, and we have this stretch of 3. All right, so I'm going to graph the point 0, 0. In a moment ago, I said negative pi over 4 and 1, but when it's stretched by 3, that's actually negative pi over 4 and negative 3. And then we'd have positive pi over 4 and positive 3. And that would actually be true, except our period changed. So I've got to start over. All right, so let's not do that yet. We still have 0, 0 because we don't have any shifting. All right, but our period is 6, which means our function actually goes 3 in each direction. 1, 2, 3. 1, 2, 3. So our asymptotes are at those two. It's 2 places. So x equals negative 3 and x equals positive 3. So now if we think about how this happens, those key points happen actually halfway between the central point we have 0, 0 and the asymptote. So that actually means that's at 3 at 1 1/2, at 1 1/2 and 1, 2, 3. All right, so we have the point 1 1/2, which is 3 over 2, 3. So it's 3 over 2 because that is a quarter of the stretch from a quarter of the period. Period is 6, so divide that in 4 pieces, 3 over 2. And then the stretch of 3 puts that point at a value of 3 instead of 1. And then mirror that, so negative 1 1/2 -3. And then we'll have this approaching those two asymptotes. And there's one period of this graph. Now, repeat this as long as you want from to the left and the right, and we'd have that. All right, number 2. Graph y equals 2 tangent of pi x plus pi, close parentheses, minus 1. All right, we have several shifts going on here. So one, we have our stretch factor of 2. We have, let's actually factor this. 2 tangent of pi, parentheses, x plus 1, close parentheses, minus 1. So we're shifting down 1. We don't have a midline, but we're shifting down, and that's our center point's going to be there. And left 1. All right, so it's shifting left 1 and also down 1. So our central point will actually be right there. Okay. So I'm going to try to change something so that won't click so often. Okay. I may not be able to change it. Okay. Well, anyways. Oh well. I tried. All right, so we'll probably have some right clicking going on. Sorry about that. So the left 1, down 1 results in this point right here, -1, 1. Now let's find our period. All right, so the period is pi over b, which is pi, absolute value of pi, so that the period is actually just 1, which means we go a half in either direction. Okay, so only half of a unit in either direction. This is a very compressed graph. All right, now we have a stretch of 2, so we know from -1 we go up 2, and actually a quarter, because we went a half in the other direction. But that is 2 from this point right here. Right? It was at -1, so it's actually at 1. So the y values of 1 and -3. 2 in either direction. And then, again, quarter of the way, so it was at a half. So it'll be at, what, -3/4, 1. And a quarter of the way from there, so -5/4 and -3. And again, we make this approach those two asymptotes. All right, and of course, go back to a calculator and graph these, make sure that it's right, but that should match pretty well. All right, so number 3, find a formula for the function below. So based on the graph, this is a tangent, also based on the part of the section this is a tangent graph. It's centered at 0, 0. That tells us there's no phase shifting left and right. There's also no shifting up. There's no the midline as we think of that with sine and cosine. But we need to think about the period. So the period appears to be -pi/4 to pi/4. So that's a total distance of pi/2. The period from our graph is pi/2. So that means we need to find b. b is pi/pi/2. Taking the reciprocal, we have pi times 2/pi. So our period is 2. Or, sorry, our b is 2 because our period is pi/2. Now, the other thing we need to know, so b is that, so I'm going to say 2 with no phase shift, it'll just be 2x plus 0, tangent of 2x at this point. Now, for the a value, we need to look at this. It's not reflected, I'll tell you that. But at this point where we're halfway between 0, 0 and our asymptote, the y value appears to be 5. And on the other side, we have a -5 at that same point. Halfway between our central point and our asymptote, value is 5, that actually tells our a is 5. So it is y equals 5 tangent of 2x. All right, now moving on to cosecant and secant, the most useful thing we can do is think of cosecant as a reciprocal of a sine and secant as the reciprocal of a cosine. So if we do that, if we sort of convert these into a different form with sine and cosine, then amplitude and period are actually affected the same way as with the sine function or the cosine function. Horizontal and vertical shifts are shifted the exact same way as the sine or cosine function. The difference is that whenever the sine is equal to 0, cosecant is undefined. Whenever cosine is 0, secant is undefined. So what that's going to look like is actually that when the corresponding sine or cosine is 0, we have asymptotes, and that actually turns into that when the peak of a cosine occurs, a secant has a trough, has a low point whenever there's a high point. So we have this trading of characteristics. All right, so here are the key points that we can deal with, or features that we can deal with for secant and cosecant. Secant will have asymptotes at negative pi over 2 and pi over 2, and key points of 0, 1, pi negative 1, and 2 pi positive 1. Key points for cosecant are asymptotes at x equals 0, x equals pi, x equals 2 pi, because sine has 3 zeros on its interval. And then the 2 points pi over 2, 1, and 3 pi over 2, 1. So let's see if we can actually graph one of these. Graph one period of f of x equals negative 2.5 secant of 0.4x. So we're going to think of this as cosine of 0.4x, so negative 2.5 cosine of 0.4x. So let's find the period. Period is 2 pi divided by the absolute value of 0.4. That's 2 pi times, let's see, 0.4 is 2/5, so multiply that by 5 over 2. So that the period is 5 pi for this graph. All right. So I'm actually going to graph, again, a cosine with a period of 5 pi. So let's put 5 pi over here, start at 0. And because we have a negative 2.5 as an a value, that means it is reflected, and it has stretched by 2.5, but there is no shifted midline. So I'll put 2.5 to minus 2.5 on my y-axis. And since it's reflected, the cosine will begin at negative 2.5. It will move to a midline, to a maximum, to a midline, to a trough. All right, now to actually find out what those values are, halfway between 0 and 5 pi is 5 pi over 2. This would be 5 pi over 4, and then that will be 15 pi over 4, if you need that. So I'm going to plot these points, but remember what I said. Whenever cosine is 0, this graph has asymptotes. So I will have asymptotes at 5 pi over 4 and 15 pi over 4. Okay, asymptotes there, and then when I have a maximum of my cosine, that is a minimum for my secant. Now I have a maximum, or a minimum of my cosine, that is a maximum for my secant, and same thing on this other side. I have a trough for my cosine, so that's a maximum of my secant. And there's my graph. That's actually more than one period. I drew a little extra there, but that is at least one period of that. Okay, let's take a look at this next question, number 5. Graph one period of f of x equals negative 6 secant 4x plus 2 minus 8. All right, so I'm going to go ahead and factor this 4 out. So that'd be negative 6 secant parentheses 4 parentheses x plus 1/2 close parentheses minus 8. And I just realized my picture was over that graph, so I'm just going to move this for a second so you can see what that looks like. And I'll do my best to not draw over there anymore. All right, so for this graph, we do have some adjustments to make. So first, we need to take and find our period. So our period would be 2 pi divided by the absolute value of 4, which is pi over 2. So from 0 to pi over 2, I'm just going to space this out and put pi over 2. Now I'm going to go ahead and split this up actually, so the center of that would be pi over 4. The next point in between there would be pi over 8. That would be 3 pi over 8. All right. Actually, I need to erase those because I didn't account for the phase shift we have, shifting to the right. We are going to shift to the right by 1/2, or sorry, to the left by 1/2. So let's put a 1/2 marker here, negative 1/2. Now that means my period is pi over 2, so let's actually, I'd like to modify this question a little, but I'm not going to. These values are going to be kind of ugly, okay? So we're going to have an endpoint over here. You add pi over 2 to this. So actually this other endpoint over here will be pi over 2 minus 1/2, whatever that value is. And we will have some midpoints in between here. I'm not going to worry too much about what they are, but there's halfway, there's a quarter way, there's a quarter way. So I'm going to leave those tick marks blank because those are kind of complicated expressions. But the real key thing is that we know how that they're evenly spaced. Okay, so we were shifted to the left. We're also shifted down by 8. So I'm going to put minus 8 down here. That is our midline. We have a stretch here of 6, an amplitude for the corresponding cosine function of 6, but it's reflected. So it is going to start at its trough, which, since we know we're going in 6 in either direction, that gets up to negative 2 and down to negative 14. So my low point is right here at negative 1/2, negative 14. Go to a midline at negative 8. Oh, midline at negative 8. That is at this tick mark right here to a peak, to a midline, to a trough. All right, now once again, wherever cosine is equal to 0, which in our case it's where we hit the midline. All right, whenever we hit the midline, we will have asymptote, and we have another on the right at our third tick mark here, where that tick mark is. And then the peaks of our cosine function are the troughs of our secant. So we have a peak of our cosine, so it's going to approach those asymptotes, and on both sides that should be true. And again, there are more asymptotes that we could draw if we needed more than one period. Now, this may not match exactly this graph, but I'm going to go ahead and actually go to my calculator and say negative 6 secant. And by the way, if you're using a TI-84, you actually have to do, instead of secant, you type in 1 over cosine of. Okay, 4x plus 2 minus 8. All right. So we have troughs at negative 2, peaks at negative 14, and that is true. Kind of have to zoom around a little bit to actually locate this one. oh, I actually missed something. I'm really glad I graphed this. Okay, the reason that I'm glad I graphed this is I actually put this point right here at 0, but actually I had already drawn the tick mark at -2, so it actually was right here. So that is a key characteristic that would be incorrect. Okay, so we have 8 going 6 in either direction, and again we've actually got a cosine looking graph there in between the two branches there. All right, so let's try to graph one period for number 6 of 0.5 times cosecant of 2x. All right, so once again, we have our period is 2 pi over b, so 2 pi over 2, which means period is pi. We have a stretch, well, it's a compression factor, I guess, when thinking about this, the corresponding sine function, 0.5 times sine 2x, with a compression. All right. Now, let's see what we can graph. There's no phase shift. There is no, the midline is 0. But we do know from 0 to pi, and again, I'm just going to put my 4 tick marks evenly spaced. All right, we know with sine, we will start at 0, so we begin at 0, and then we go up and down 0.5. So we have our peak, our midline, our trough, our midline. But wherever sine is equal to 0, we have an asymptote. So there are 3 asymptotes for this one. All right, and then we find where our peaks are. That is a trough for the cosecant. Where our troughs are for sine, that is a peak for secant, or cosecant. So if we can think about the sine function, we can find those key points for our cosecant. If we can find the key points for our cosine, we can find our secant key points. Okay. Number 7 says graph. It's got this cosine graph is given graphed, and it says sketch the graph of the secant graph that corresponds to that. Well, that's actually really easy because we know that we have wherever the cosine is at its midline, which this midline appears to be at 1, wherever we hit that, we have vertical asymptotes. So everywhere we see a midline, I'm going to draw asymptote. All right, and then we know at the peaks of our cosine correspond to troughs of our secant, and troughs of cosine are peaks of our secant. So there, I can actually sketch it right on top of that, and that is the entire exercise. All right, so finally we get to move on to cotangent. My suggestion here is when we have cotangent, we identify the stretch, we identify the period because it's the same as tangent. I suggest you draw a graph of tangent and then use the reciprocal relationship to actually figure this out. So that's what my kind of suggestion would be, to think about that. Whenever tangent is 0, cotangent is undefined, and vice versa. And if you have shifts, be sure and deal with those. So let's see, we've got, let's actually not do these. Let's do number 9 right here. So it says, sketch a graph of one period of the function 4 cotangent of pi over 8x minus pi over 2, close parentheses, minus 2. All right, so this one's a little more complicated than the first one there. But if we first go ahead and factor this, so I'm going to say 4, and I'm actually going to think for tangent. If I factor a pi over 8, that's our b, parentheses, x minus, and that would be a pi over 2 divided by pi over 8, that would be 4. Yes, if you distribute that, that would actually work. Close parentheses, minus 2. So we have a shifting to the right by 4, down by 2, an amplitude or a stretch of 4, and a b value of pi over 8. So, okay. So if we take that b, we can say that's the period, well, pi over, here, period is pi over b, so that's pi over 8. That's pi times 8 over pi, so 8. So our period is 8 for tangent and cotangent. We know we're shifted to the right by 4, so I'm going to go ahead and start there. So 1, 2, 3, 4, and down 2. So 4, negative 2 is our, should be our central point there. Now our period is 8, which means that we go 4 in either direction from that point, and those are our asymptotes. 1, 2, 3, 4. And then halfway between those we have our other key point. So let's see, that would be at 2 in either direction and stretch of 4. So we go right 2 and up 4, which is at positive 2, and so we'd have at, what is that, 6, positive 2, and that would be 2, negative 4, and that would be our tangent. Now, just because we haven't done too many of these, I'm going to actually go ahead and graph 4 tangent pi over 8 x minus 4 close parentheses minus 2. Alright, so 0 to 8, we have a central point at 0.4, comma 2. Enter parentheses 4, comma 2. 4, negative 2. 4, negative 2. Okay, that is our central point. Just making sure, okay, the asymptotes all line up. Okay, so this would be our tangent graph. So cotangent, whenever tangent is at the midline, we have a cotangent that is undefined. So let me just draw that. Tangent's at the midline. I shouldn't call it the midline, but when we have that central point where it's 0, that would be a 1 over that to the undefined. And cotangent is going to be 0 whenever it's undefined. So that'd be at those two places there. All right, and that gives us something. So based on the shape of this graph, it'll actually approach this asymptote coming, it's not reflected, so coming from this way, we're going to do this. So we'll have something like this and come down right over here. So that should be what our graph looks like. So once again, for cotangent of pi over 8, parentheses, x minus 4, close parentheses, minus 2. All right, they actually have this interesting crisscross pattern that occurs with the graph too. So we've got a vertical asymptote where it's 0, yes. Okay. Or right to the midline, that is. All right, so I think that looks pretty good. All right. So I think that, like I said, I think that looks pretty good. So I'm just going to leave that the way it is. Okay. Now our last question is determine the equation of the graphed function. So now that we have graphed all of these, hopefully we can tell very quickly that this is not a tangent or a cotangent. All right. And what we have to do is actually look when we're seeing this. We can actually find the midline, look at the peak and the trough, and find halfway between there. So this has a peak of -4 and a trough of 2. So that looks like -1 would be the center of that. 1, 2, 3, 1, 2, 3. All right. Now, wherever the asymptotes are tells us that this function it's a reciprocal function, so it's going to be 0 there. It'll be at the midline there. So we've got midline at 1, -1, and it looks like we'll have a peak at 0, 2. And then it looks like we just continue that pattern. Okay, so I've already got an inclination of what this graph might be. Because it starts at a peak, I'm leaning towards being a cosine, which means that it would actually be a secant function. So we need to figure out what the amplitude is of the corresponding cosine function. And it appears that amplitude was a 3. So this would be 3 secant with no shifting, so something x, we'll have to find b in a second. And the midline was -1, so it's got a -1 at the end. So now if we take our period, if we continue this pattern out, it appears it repeats every 4, from 0 to 4. So our period is equal to 4, which means b is 2 pi divided by 4, which is pi over 2. So we'll have a pi over 2x. So 3 secant pi over 2x quantity minus 1. All right, and that is the end of 3.6. So I hope this is really helpful as you're getting through your assignment for this. Remember what those graphs look like. Go back through here and look at that.